All right, thank you everyone for coming. For Team 3, we're going over the robotic tool supplier. My name is Mario Carvajal.
Jorge Silva.
Pedro, Chaviano.
Alfonso, Jarquin.
Let's get started. So our initial goal was to make a ball-type robot, a sphere, that can assist people in basic tasks, can hand them tools, and basically assist anyone that could need help on the job. We chose, initially we wanted this to be automated, but we saw that was going to complicate it a lot, so we decided that we're going to go with a remote control prototype for now. So, in our research, we found that the benefits of a spherical robot is that we have a large wheel diameter radius, and we are able to overcome large obstacles. And since for example, since the shell is self-contained, all the components are inside, it's easily able to waterproof the shell, and it can overcome water obstacles such as those. Also, the uniform structural of the outside, can help over uneven terrain and stuff of that sort. So we also used flywheels to stabilize the sphere. That was one of the things that we came up with. And there were 3 main types of spherical robots, which we'll go into more in depth. These were the 3 choices that we had. We had the internal car, also known as the hamster ball design. So there's an RC car on the inside that rolls the whole sphere. The downside of that is if you hit an obstacle or something, the car tends to lose friction with the inside of the surface. So that wasn't a good, right away that got rid of that choice. The next one is the pendulum turning control. This uses 2 drive shafts to roll the sphere and a pendulum side-to-side motion to rock the sphere and allow it to turn. Then the last one is the multiple mass shifting. This one has a bunch of different masses placed in certain spots on the sphere to coordinate and move in unison to allow the rolling motion. This one was very, very complicated, so we chose not to go with that one. And next slide. We chose to go with the internal pendulum. So we chose the internal pendulum. It has 2 flywheels turning in opposite directions to help stabilize the sphere. And also, by turning the pendulums, we can get gyroscopic precession and for added torque to overcome obstacles such as like a small step to roll over. Obviously, the pendulum turning helps to roll the sphere, and like I mentioned, RC systems to control the robot. So these are some of the standards that we use while designing this robot. We use the American Society of Mechanical Engineers for all our metric systems and safety standards and that type of stuff. The International Federation of Robotics, the Institute of Electrical and Electronic Engineers for all our circuitry, and the American Gear Manufacturers Association to ensure that all our gears are not going to fail, and as well as the American Bearing Manufacturers Association for our bearings.
So there's 3 main building restraints that we had to focus on and avoid. One was building in a compact space. The other one is to have the flywheel actually leveled and centered to the spheres. And the third one is the weight of the robot so that the shell can hold on to it. So as you see, this is our final prototype, our CAD drawing. So you can see to the right, we have the pendulum moving left and right, and it works really well when you're moving around like 1 to 2 miles an hour, moving left and right. Then you can see to the left and right are drive pulleys. And then we have our tool supplier that has connected to the spring. The spring is not connected to the tool supplier, it's actually connected to the other side of the door. We made some changes of modifications at the end to have 2 lips open so that we have 4 options whenever we want to supply the tools. And then to the right, you can see the 2 flywheels. One of the constraints we had was where to level the flywheels, because if we dropped it too low, then it would hit the bottom. We would raise it to the middle, it would hit all the gears and stuff. So we were really messing around with where to place the flywheels and distribute all the weight to keep it balanced. And here's the final. And you can see we have also like 4 hinges on each side of the rims. And the rims are actually 3D printed, and it withstands the weight of the sphere. So this is some of the process of building the prototype. First, we got the brass cast iron flywheels. We had to machine them, and after machining them, balance so it's precise, because when it's running at 18,000 RPM, any misalignments could torque the robot. And destroy any moving components. And you can see this is the gear, double gear to the 32 gear. We have the pendulum with the servos. This is our first prototype with the 3 channels, but when we realized when we tried to fit it in, it wasn't working the way we wanted to, so that was our first prototype.
Okay, so we did a couple stress analyses to determine which of the parts would be most crucial in our design. Primarily, one which we were concerned about is the Supplier, which is in the upper right and the bottom left photos. Running at 18,000 RPM is a lot, and we actually had to bring it down. Originally, the battery we had was too powerful to power it, and we actually ended up at 22,000 RPM. We brought that down to 12 volts instead of 18 volts, and we ended up at 18,000 RPM. Currently, this is the stress and the factor safety analysis from each flywheel. We just wanted to make sure that it wasn't going to break from the actual mount, which is from a drill motor. It's a DeWalt 995 drill, if you're interested. It's incredibly torquey and provides enough force to actually roll the ball onto itself, along with the motors which we had originally chosen. Second was the channel stress analysis, just to determine whether it was going to buckle under the torque from the motors which were driving it. So pretty much with the torque going inverted, it's pretty much bending the shaft up. We just wanted to make sure that it was going to stay steady and not warp the entire thing. Our factor of safety for the actual channel ended up being around 17, so we're well within the bounds of what we want to be. Second was the motor mounts, which were 3D printed. That was a little hard to do because of the fact that we were so restricted in size. So we had to make it a very compact design using the actual meat from the printed design and just drill it right up into the channel. Once we did that, we used the same torch to determine if they were going to snap at the very edges, and again, we had a factor of safety where we were in a reliable setting. So we had a couple of design constraints while creating our initial prototype. First being the shell. We wanted to make sure that it wasn't going to crack under any stresses. Through our whole design process and the learning experience which we had, we actually found out that the shell which we had purchased, a 20-inch shell, is not the one which we had received. We received a 17-inch shell. So our design shrunk a little bit, and we had to pretty much work with what we had and giving the fact that giving it for 2 months just to get the 17-inch shell. After that, the second one we had to do was the drive motor. We wanted to make sure that the force of stress was reduced enough to break the internal components, but we wanted to make sure that it was going to drive in the first place. Our initial reduction was around 6.5 from the drive motor, but we ended up with 8 reduction factor of 8 to make sure that it had enough torque to spin the actual ball. Next was the racking pinion, which is initially delivering the tools. It has a center servo, which just spins them outwards and delivers the tools. We wanted to make sure that it had enough power to open the doors and not get stuck on any of the springs which are holding the doors down. The second was a flywheel to make sure the vibration wasn't going to be enough to shatter the shell or destroy the mechanism on the inside. We wanted to make sure that it wasn't going to be off balance, which is why we had them precisely machined after we had purchased the flywheels. We have analyses from that balancing mechanism which allowed us to machine the flywheels properly to make sure that they were perfectly centered balanced. And upon measuring their speed with the tachometer, we realized that they are sensitive enough to be altered by as much as a piece of tape. So they are very precise machines. Here's some of the design steps that we had. How I mentioned before, how the steer was our main concern, making sure the holes were centered and it wasn't going to crack. That was our first big design problem which we had encountered, making sure the holes were centered. Initially, the steer came with one 5-inch hole on the side, and we had to expand that hole to 10 inches in diameter. After we did that, that was going to be our new center. Once we had found our new center, we had started to build the inside because, as we found later, we couldn't progress one step as we wanted to. So we had to do everything kind of together. After we made the initial 10-inch hole, which is right here, we had to start building the shaft on the inside. After the shaft was on the inside, we knew the shaft was straight. So as soon as we mounted it on the other end, we had to draw that line and cut it, which is our new center. So if you view a before picture, which is pretty much right there, you can see us cutting the initial hole, and that's exactly where we had to pretty much start. So again, how Mario mentioned before, we did not just do an automated robot just because of time constraints and the complex features that we have here in our robot. So we chose an RC system. We chose the DXM6 6-channel Spectrum radio to control of our systems, and through our design, we were actually able to bring those 6 channels which we were originally going to take over, which was 2 drive motors, 2 flywheels and just 1 channel, flywheel tilt, pendulum tilt, and arm control. We were able to bring that down to 4 channels. using a Y splitter for the motors, which is controlled from one hand, and using a manually operated switch to control the flywheel. So we went from 6 down to 2. So in experimentation, we had a couple of problems that we encountered. Primarily, which was overheating of the batteries, which is essentially just making sure that they can run. By overheating of the motors, asserting that they can run the entire system without frying. We noticed that it was too much voltage for the receivers to handle 2 batteries at once. So we had to modify some bits of our receiver to accommodate the things that we had. The second was the speed test. We wanted to ensure originally that the robot could follow at around 5 miles per hour. We realized that was a bit of an overshoot, although it can travel 5 miles per hour. It's a bit difficult to control because of the weight of the pendulum and the fact of the torque that the flywheel produces. Now, turning radius is another one. We realized that you cannot essentially just turn the radius the robot on itself. Instead, what you have to do is use the pendulum in combination with the motors, which was able to maneuver around how we wanted it to. Then terrain, we tested it on asphalt, concrete, carpet, grass, and it ran well enough. And here's some of the data which we had. Again, 18,000 for the flywheels. Total is around 30 pounds, the robot, which is a weight where we wanted it well to be. Originally, our estimate was 50 pounds, so we were able to shrink that down enough. Then the 3 mile per hour speed, which is a comfortable controlling speed. And then a pretty much weight of the tools, which you can put pretty much anything you want up until about 3 pounds, which then is up there.
For a cost analysis, originally our budget was around $580, and at the end we spent around $1,300. Most like we divided the main components into 3: the electronic part of the robot, the flywheels, and then the gear rack and the main channel. For a global design, we want this tool supplier to be able to assist different kind of professionals in their respective fields of work, like professors in a classroom, doctors in a hospital, like others. This robot can be used by any of us to assist another one in a remote location to simplify a task or work. We want our project to be open source for people to be able to personalize their own tool suppliers. And we think that because of the type of robot, this tool supplier can actually even be used to assist people in disasters or emergencies. For our learning experience, we worked really well as a team. We got to experience actually machining and building and disassembling all the components and elements of the tool supplier. We had to manage our time to be able to meet the deadlines. We realized how the design sometimes worked and sometimes didn't in different aspects of the process of manufacturing, and the testing experience was really challenging. On the Gantt chart, we divided it in 2 parts. Like for the first semester for design, senior design 1, we went up to the CAD drawings. That's where most of our time was spent on designing and selecting all the components and the main designs. And the second part were the simulation of the certain elements for this robot to work, and then optimization of those components, the validation, and the testing. Of division of responsibilities, Pedro was responsible for the design concept. Alfonso took care of the simulation. Mario went over the construction and testing, and I kept a look for the financial organization. We need to say that we all came together and help each other in our individual tasks. For our conclusion, we were able to build and test this robot as much as we could, not as much as we wanted. We kept a reasonable budget for the robot. The design proved to be reliable and durable. We want, as we said before, we want this project to be open source for people to be able to personalize their own designs. For our future work, we want to automate it. We want to change the shell for a thicker shell. we wanted to make it waterproof, and we think that we can actually expand it or contract it, whatever the application requires. Thank you.
Would you like to open it up for questions?
Are you gonna demo it?
Yeah, we can run.
Roll it around the floor?
We asked Dr. Tosunoglu, and he said later on during the break we can run it outside.
Okay.
The thing is that the flywheels are really
Really loud, yeah. So, any other questions? Yes.
So you said it can hold 3 pounds.
Right.
What would you have to do to make it hold 20 pounds?
Well, we'd have to increase the size of the robot, and
Only-
also
Only the size of the shell, or would you have to?
most of that depends on the shell because the shaft is very strong. It's made out of aluminum, like very strong aluminum, and
And it's
basically,
connected to the ball bearings that's holding the stress.
yeah.
Like the ball bearing bracket that's connected to the main channel also. So that's taking the stress. It's not on-
Because at
on the
20
shaft.
pounds, I can put a toolbox in there.
Right, exactly. And
Or
that's why this
emergency first
can be
aid kit.
scaled up and down depending on what the application is. And most of the stress is here on the actual
The
mount to the sphere. So if you want to increase the amount that you can carry, you have to increase the thickness of the shell so it can carry more loads.
Along with increasing the thickness of the shell and the size of it, we also need to increase the range in which the pendulum spins, because that 20 pounds is a humongous added torque on the actual arms of the robot. So on top of, just making it bigger, you need to increase the range in which the pendulum spins, which is actually set right now to the center pendulum.
Okay, cool. Tell me about, you made a statement that your testing was challenging.
Yes.
So talk to us about
So,
what was challenging.
like we said that originally that the shell was supposed to be 20 inches in diameter when we bought it. Our flywheels were supposed to go underneath, so the center of mass is below the drive shaft. And we noticed that with this smaller shell that wasn't going to be possible. So we had to move the motors for the flywheels up to the top, and they're up here. So that shifted the center of mass
Center of
up,
mass.
and it started to spin on itself. So we had to go and add in weights at the bottom, and that really complicated our testing a lot, yeah.
And that's a positive engineering experience.
Right,
That's
yeah.
reality. kind of.
Exactly, yeah. A lot of working on the fly and then
Every problem we
adjusting.
ran into, together as a team, we solved it.
Yeah.
We ran into every step. We had a problem. A major problem, a big problem. The shell cracked 3 times. We fixed it twice, and every step we had, it was all teamwork together in this robot.
Yeah.
Good, thank you.
Did you write all that down? We had this problem, we solved it. We had this problem, we solved it. We had this
That'll
problem.
be too long.
Yeah, we can put that
But
together.
in the end,
Right.
that's interesting.
Yeah.
The historical, process that
Right.
you went through to get to the end.
Yeah. We didn't think of that. Yeah.
Those are the doors that were 3D printed.
So this is how we centered it at first, because we had a centered, the middle is precisely centered through G code, so we can put a shaft that's straight down, and then we can level it with a level to get it precisely up.
And that's how we got the holes for the sphere.
And then that's the final concept of 2 splits that go up and down. And that's how
That's us trying to level the shop, trying to get both holes in the center. In the end, what we actually did was the brackets actually have a little bit of clay, so any mess ups that we had in initially cutting it, we were able to make that up through the clay in the bracket, so we were able to get just a millimeter up, and that was enough to make it work.
So could you make that shop tough? I mean, could I have that in my machine shop? And,
Well, yeah. If we could make the shell out of metal, that would help out a lot instead of using the acrylic.
the gal that runs my tool crib, somebody wants 4 end mills. Could it be conceivably designed and, fixed up, tilted a little bit more, and she'd load it in there and then zip it over to one of the machinists?
Yeah, we want it to be automated, that it balances itself. So if we remove a tool from one side, it can
The
balance
pendulum
itself.
can balance it.
Yeah, and then so we can actually compare
At that high RPM, when you're turning the flywheels, it wants to keep center the whole time. So depending on the weight, you just have to put a counterweight on one side of it. So we were thinking maybe to adjust the length of the motion of one side if we put way too much weight on the other.
That's
This is the flywheel, the motor, testing the motor. So you can see how fast it's going.
But that was before we got the gear touch.
Yeah, that was
Here we
one
go.
change that they got.
This is the test run, our first test run. This is just with the drive shaft. This is without the pendulum, the flywheels. And we ended up smoking with the red motor, because
Yeah.
the motor, the circuit, we had too much power coming in. This is with everything in the sphere, but the weights are not on the bottom, so it's not leveled.
Yeah.
So the flowers are upside down.
Flagler's one turn.
And you can see how there's no friction on it, and it's really hard to start the motion at first. So that's why we started putting the rubber on the top. And it's really challenging building it because you only had a constraint of the sphere inside while you're moving all the nuts and bolts. And you can see the strip we had. Now this is complete flat ground. So this is our first test run with everything on it, and it's going to take a little bit because just like any regular RC helicopter, you can't just pick up a control and fly it. You have to practice and get comfortable with the vehicle. So that's the tools supplying on both sides. You can see that the flaps open and close automatically.
So you need a pilot.
Yeah, well, for this version, I mean, if it's automated, then it can handle it on itself.
It's not creating enough friction on the floor, so it's rolling itself inside the sphere. We didn't get a good test video of it, rolling completely, because at the end, the sphere cracked, but we were able to fix it, but we weren't able to get good lighting on the video, so it wasn't good high quality. That's it.
Okay.
Thank you.
Any other questions?
Do you have blueprints of the entire way you made this?
Well, since the design changed so much, I mean, we would have to do it now, like with this design that we have right now. We have the initial CAD drawings, but that is, it's a lot different than what we have right now.
So you didn't make changes to the print as you went?
Yeah, no, we just went, as we went, hitting new obstacles on the way.
But it was definitely, if we didn't have the print previously, we wouldn't be able to come up with.
That was a good starting.
Many of the calculations and the purchase that we made were based off of tiny shell. So by the time we figured out that it was smaller than what we had ordered, it was too late to go back and redesign everything. So we just had to live in the moment and go with what we had.
Okay, thanks guys.